Now the Juan de Fuca plate is pretty interesting because it used to be part of a larger plate. There was originally this Farallon plate that was being subducted underneath all along the western coast of North America. If we go back 100 million years, this Farallon plate was being generated at these mid-oceanic ridges out in the middle of the Pacific Ocean, and the entire western coast from British Columbia and Canada all the way down to Mexico was a subduction zone. Looked like the coast of Oregon and Washington. Over time, that Farallon plate has been getting subducted, and what we see today are simply the remnants of that plate. 30 million years ago, the Farallon plate was getting subducted all along the North American plate boundary. But then 20 million years ago, the mid-oceanic ridge started to become subducted. As that occurred, a subduction zone plus a mid-oceanic ridge results in a transform boundary. San Andreas Fault began, and as more and more of that Farallon plate got subducted, the San Andreas Fault got larger and larger. So now we have the Juan de Fuca plate to the north and the Cocos plate to the south that are both being subducted, but between these two plates there's nothing but a transform boundary. So here's our configuration today, showing the subduction that's going on down off coast of Mexico and Central America, and to the north in British Columbia and Oregon and Washington, there's that last remnant of the Juan de Fuca. If we zoom in on the San Andreas Fault, we can see evidence of this transform energy continuing over time. This is a map of the San Andreas Fault system throughout California, and we can see that there are segments that slip at certain times while other segments don't. In 1857, there was a fairly significant earthquake that occurred along this kind of central portion of the San Andreas Fault through the Carrizo Plain in central California. In 1906, the big earthquake occurred along the San Andreas Fault in San Francisco, but it didn't completely rupture the entire fault line. Each of these different fault segments displayed different behaviors. And the best thing that we can do with this is use this information in order to guess which fault segments are going to rupture in the future. The longer they've been sitting quietly, that means the more stress has been built up between these two blocks, and that means probably the bigger the earthquake could potentially occur in the future. If we zoom in on San Francisco, we can see that actually even within the San Andreas system itself, there are multiple faults. Through downtown San Francisco, that's certainly where the San Andreas Fault runs, and that was where the big rupture occurred in 1906. But there is a parallel fault called the Hayward Fault that runs through Berkeley and Oakland inland of the bay. But even though we kind of refer to it as one big fault, there are both large numbers of segments within the San Andreas Fault and large numbers of parallel faults that can generate earthquakes at any given time. One interesting characteristic of all these faults is that they are all transform boundaries, so we can often see the offset that occurs on one side of the fault to the other. All along the San Andreas, we see evidence of this offset, and at one point this stream channel was running down this little valley, and it probably crossed the fault and continued to go straight on down. But over time, creep and these earthquakes have driven this lower block to the left while the upper block gets driven effectively relatively to the right, and over time these stream beds have been offset, and that is the kind of evidence that we like to be able to see in order to see what kind of movement has occurred in the past and predict how much movement is going to occur in the future. When we try to predict earthquakes in the future, the best that we can do is, of course, use this information from the past and apply it to our likely future scenarios. The best place where this has occurred is called Parkfield, California. It's a segment of the fault that regularly had earthquakes for a long period of time. From the 1850s, there were lots and lots of earthquakes that occurred at regular intervals. They tend to be somewhere around a magnitude 6, maybe a little bit higher, but regularly went off every 20 years or so. The way to map this out is to actually trench across the fault and map the layers that are offset from earthquakes that had occurred in the past. So once you find the fault, you can actually see layers where they break and cut across each other. And what we found there is that in 1857 there was a big earthquake. So there's a large offset that occurred, maybe as much as 50 or 60 centimeters. And then nothing occurred until about 1881, and then a large scale offset occurred, again about 50 centimeters or so. 1901, 1922, 1934, each of these events showed very similar slips after a very similar period of time. Each of these events that occurred were very regular and very similar to the ones that occurred in the past. So the best guess was that 20 or so years later, there would be an earthquake. It turns out it took way longer than that. We didn't get an earthquake in Parkfield until 2004, but because the USGS was so prepared for these events, they actually put up cameras and seismic monitoring equipment, every sort of device you could use to monitor along that fault. And as a result, we have a video showing an earthquake occurring. I'll play it for you now. Time lapse until the earthquake. There is our magnitude 6.0 earthquake occurring along the Parkfield fault. Not very impressive, huh? Turns out earthquakes aren't what kill people. Falling buildings are the things that kill people.